We'll continue. We'll see the second part of this work energy principles. Okay. Rule number 20, I'll check with the participant list. Okay. I have a track of participant list. So if you have missed, then I'll cross check in the participant list. 32. Okay, let me share my screen. Screen is visible? And please mute yourself. Okay, when you join and don't unmute. It starts echoing. CR, please ask others to join the class. Roll number 119, mute yourself. Okay, let's start. Okay, how many participants? 43. Kind enough. Okay, let's start the class. Okay. Please respond to the chat box. Audio and video is okay. Okay, let me try once again. Now,
In lecture SA 19, work energy principle was introduced and its application for calculating truss displacements was illustrated. In this lecture, I'm going to examine the use of this principle
okay.
for calculating deflections in beams and frames. Make sure you have reviewed the previous discussion before continuing with this lecture. According to work energy principle, work done by applied loads equals to the change in the internal energy of the structure. Assuming
So external was now external was equals to change in internal
that the
energy.
unloaded structure has zero stored energy, we can write external work equals to internal energy.
Or you can say external
In the
work
case
is
of a
equals to
beam
internal
subjected to
energy.
a concentrated load
So beam is
P,
given, you are applying a
external
load,
work
it gets
equals to
deflected.
1/2 P times delta, where delta is the vertical displacement.
Last class we saw that external work will be half P into delta. When we plot a load versus a deflection curve or displacement curve, we got a straight line, right? So by that we can say that if we sum up all the deflection over a beam, then we'll get the overall external work done by that member.
Under the load. Let's see how we can come up with a mathematical expression for internal energy for this beam. Imagine the beam is divided into small elements, each carrying an internal bending moment like this. Each element undergoes a small amount of deformation caused by the internal bending moment. Let's refer to this deformation as d theta. We can write the internal energy stored in the element as 1/2 m times d theta. If we sum up the internal energies in all the beam elements, we get the total internal energy. For the sake of accuracy and convenience, we generally perform this summation via integration. That is, total internal energy in the beam is 1/2 times the integral of m d theta. Let's see how we can evaluate this expression.
And
I know how to write m in terms of x since
now they
m
have
is the moment equation for the
earlier we
beam.
saw they relate
Here is the moment equation for a
they
beam of
relate the
length L.
external internal energy with the load. Okay, now they are relating the internal energy with the moment. Okay,
L subjected to a concentrated load P at midspan. So
to find the displacement, you can relate with the load. To find the slope, you need to find the moment. Okay,
I can write the beam's internal energy as, since m is defined in terms of x, before I can integrate this expression, d theta must be replaced with dx. But what is dx and how is it related to d theta? Here is a beam element before deformation. We refer to the length of this infinitesimal element as dx.
so they have taken a section of this beam and considered it as dx.
Here it is after the deformation.
This is before this. This one is before deflection. This one was before deflection, and this is they have deflected and enlarged the section to show the variation. Okay,
Note how the top part of the element is compressed or shortened and the bottom part elongated. Since we are going from compression to tension, there must be a plane between the top and the bottom fibers that remains undeformed. In two-dimensional drawings, we refer to this plane as neutral axis. What is the length of the beam segment along the neutral axis? Given that this length does not change as the beam deforms, it must be dx. Now we can write dx in terms of d theta. From basic geometry, we know that an arc length of a circle equals to the radius of the circle times the angle facing the arc length. Here the arc length is dx, the angle facing it is d theta, and the radius of the circle is r. So we can write dx equals r d theta. Note that r is inversely proportional to m. As m increases, r decreases, and vice versa. Not surprisingly, the product of m and r is constant. For linear elastic material, this constant can be expressed in terms of modulus of elasticity of the material and moment of inertia of the beam segment about the axis of bending. More specifically, we can write m times r equals E times I, where E is modulus of elasticity and I is the moment of inertia. Since dx equals r d theta, we can write d theta equals dx over r. And since m times r equals EI, we can write 1 over R equals M over EI. Then d theta
Basically, this is from pure bending. We studied in our earlier classes, right? The pure bending moment equation. So this is m by ei by 1 by r. This r is your radius of curvature. So see, everything is related in the subject. So if you are clear with that concept, or they have shown the little derivation of this, the pure bending equation. Okay.
equals M over EI dx. Now we can write for our simply supported beam, we can write assuming a constant EI for the beam, we can write or therefore the expression for the work energy principle becomes we can use this equation to determine delta.
So this is the deflection for a simply supported beam with point load at the center. So see, if I use for the method of deflection, slope deflection method, I'll get the same value, PL cube by 48 EI. Okay, the methods are different. The value will be same at the end. Okay, that for simply supported beam with point load at the center, you will get the deflection PL cube by 48 EI from both the methods.
Let's wrap up our discussion on the work energy principle by examining its use for determining the deflection of a frame subjected to a concentrated load. The expression for external work is
Frame
rather
is
easy to
not in your
obtain.
course, but let's discuss frames also. Okay, as we are discussing this method, let's discuss the frames also. So this is a frame. Simply supported frame. One support is at one support. It is supported at a roller at one end and hinged at one end. Okay.
It
Portal
is
frame. This is
1
also
half P
called as
times
portal
delta.
frame.
The frame consists of 3 members. We need to calculate the internal energy stored in each member. To do so, first we need to
So we
analyze
have
the
to divide the
structure.
energy. We need to find energy in the member AC, then CD, and then DB. So we have distributed this internal energy. We have distributed in three members. Okay.
And calculate its internal member forces. We start by applying the equilibrium equations to the entire structure.
See the moment of inertia. Okay, very important. These two values are very important in mechanics of material. E, I, modulus of elasticity and the moment of inertia. Okay.
Here is the system's free body diagram.
This one thing I want to share, that this E will be the material behavior. This depends on your material behavior or the material type. You can say material behavior or you can say material type. Okay, for different material it will be E value will be different, and this I depends on your shape, plane figure or unsymmetrical symmetrical figure, like rectangle, square, circle, square, triangle. Okay, this I value will depend upon the shapes, and this E value will depend upon the material behavior, you can say, or you can mainly material type. So for steel it will be different, for concrete it will be different, so for rubber it will be different. So this E and I is very important parameter of a material or a structure, or a member of a structure. So first
There
of
are
all,
three
as we used to find the reactions in a beam or in a truss, so we need to find the reactions in frames also. Okay, so they have found out the reactions. As it is roller, we know for a roller only vertical. We used to have only vertical reaction, so they have represented it by By. And for the hinge supported, we know we have two reactions. One is Ay and another is Ax, right? And this is the load is applied.
unknown support reactions. We can calculate them very easily.
So as in the same way,
Now we are
as in the same way, we used to find the reaction first. So in frames also, the first step is to find the
ready
reactions.
to
Okay.
calculate member forces. Let's start with member AC. We know the forces at A, so we can apply the equilibrium equations to the entire member in order to determine the forces at C. That is, for AC, sum of the forces in the x direction must be 0. Sum of the forces in the y direction must be 0. Sum of the bending moments about, say, point A must be 0. So we get,
So they have separated the systems to find out the forces in on those
now
members.
draw
Okay.
joint C and balance the forces at the joint.
So basically, they have
We know the
related the
forces at
forces
the
with the
column
they have related the forces with the energy. Okay, and movement with the
end.
slope and energy.
The forces at the beam end are opposite to those at the column end. These also balance the forces at the left end of member CD. So the free body diagram for member CD looks like this. Next, we examine joint D. Here is the free body diagram for the joint. The forces are balanced, so we can move on. Lastly, here is the free body diagram for member BD. The member carries only an axial load. Now that we know all the member forces, we can calculate the internal energy for each member. Let's start with member BD. The member is subjected to an axial force only. Therefore, the member's internal energy can be written as the axial force in the member is negative 2p. We use Hooke's law to determine the member.
So in frame, your internal energy is calculated half axial force by axial deformation, and in trusses, right? In method of joints, we see in the trusses it was member force into the member deformation. So for different structure, or you can say so like a truss, beam, and truss, beam, and frame, your internal to find the internal energy, it has different values. Okay, for frame it will be axial force and axial deformation, and for it was truss, it was your member force and member deformation, right?
Member's axial deformation. See lecture SA 19 for details. The internal energy stored in BD is Next, we examine member AC. The member is subjected to three internal forces: an axial force, a bending moment, and a shear force. Each force causes a unique deformation and therefore contributes to the total internal energy of the member. The axial force causes axial deformation, the bending moment causes rotational deformation, and the shear force causes shear deformation. So, the internal energy of the member can be written as the sum of three terms. However, shear deformation in beams is generally negligible. Therefore, let's omit the last term. For the axial case, we basically repeat what we did for member BD. To determine the internal energy due to bending, we need to write the member's moment equation.
You can write this derivation in your copies also. Pause the video and write in your copy later on.
So the internal energy due to bending can be written as, therefore the total internal energy stored in member AC is. Finally, we consider member CD. Like AC, this member carries an axial load, a bending moment, and a shear force. Ignoring the shear deformation, the internal energy in the member can be written as the sum of two terms: internal energy due to axial force and internal energy due to bending. For the axial force, we have for bending, we have this gives a total internal energy for member CD. Now we can write the structure's internal energy as the sum of the member internal energies. By the way, this portion of the internal energy is due to axial deformation, and this portion is due to bending. The equation for the work energy principle can now be written as solving for delta, we get the horizontal displacement under the applied load. In this lecture and the previous one, we saw how the work energy equation can be used to calculate displacement in trusses, beams, and frames. This application of the work energy principle, however, has limited use. Do you know why? You see the limitation. Here is a beam subjected to a concentrated load. The work energy equation for this beam is, assuming that we can determine the internal energy, the equation can be used to calculate delta. This is so because delta appears in the expression for external work. If the displacement that we seek to determine does not appear in the external work expression, it cannot be calculated using the work energy equation. For example, vertical displacement at B does not contribute to the external work here, so it does not appear in the work energy equation. Therefore, it cannot be calculated using the equation. Here's another example. The work energy equation for this beam is 1/2 times T delta plus Q delta star equals to the internal energy. Here the displacement at B does appear in the work energy equation, but still we cannot calculate it.
Sorry.
Why? Because the equation has two unknowns, delta and delta star. We cannot solve for two unknowns using one equation only. Simply put, the work energy equation can only be used to determine the displacement under an applied concentrated load in the direction of the load when no other applied loads are present. Although this technique has limited practical use, the work energy principle is a basis for more general energy methods. We will study one or two such methods in future lectures.
So that was about this second part, okay? So go through these two recording classes once again to understand clearly, and you can write your roll number in the chat box. You can write your roll number in the chat box. Please go through these videos, okay? Everyone wrote their roll number? Anyone left? Last was, where do you see? Okay, thank you.